本日は大村義治教授、ご退職記念スペシャルセミナーで、題目は、Computer Simulations of Waves in Space Plasma です。英語でご発表いただきますが、日本語で質問やコメントいただいても構いません。Let me start today's special seminar, RISH Open Seminar. The speaker is Professor Yoshiharu Omura. The title of the seminar talk is Computer Simulations of Waves in Space Plasmas. The working language of this seminar will be English, but questions and comments in Japanese are also welcome. I look forward to your active and vocal participation.
Can you see the slide?
Yes.
Okay, let me start. Thank you very much gathering for me for this seminar. I'd like to present my efforts of computer simulation in the past nearly 40 years. And anyway, I collected videos from my computer disk, and all these video and simulation results are from our supercomputer KDK system. So I really appreciate the support for this from this institute, RISH. I will be presenting the simulation result, and simulation is so-called PIC, PIC, particle in cell simulation, where we solve the basic equations of the motions of many particles. Actually, we will solve the maximum 1 billion particles. And we solve the electromagnetic field by using the Maxwell's equations. And we mix the solution of this equation motion and the field equation for a small time step delta t, and we repeat it many times to see the evolution of the electromagnetic field and particle dynamics. And I will present mostly the two different topics. Say, this is electrostatic solitary waves observed in space, in various regions of space. First report of this kind of wave, solitary wave, is made by the geotail waveform capture, and this can be explained by the particle dynamics. I will show you shortly. And to model this kind of particle dynamics, let me show you the simple model of the physical system, physical process. This is not exactly the real simulation. Okay. Just let's think of the case, so-called Langmuir wave. This is electrostatic wave, most fundamental wave in plasmas. And it can have the oscillation at plasma frequency, so-called electron plasma frequency, and with different wave numbers. So it contains different phase velocities. Since the simulation system is discrete, the phase velocity can be discrete like this. Then we have the wave field EW, electrostatic field in the x direction. And in addition, we assume the constant E field that is acting all through the system. Then the equation for the particle dynamics becomes like this. This is the velocity and position. And here we have the sinusoidal sine function, trigonometric function. And this is the wave amplitude. Since we may assume many waves, we have a summation of the waves. And then we have external E field. This is a very simplified system. And if we define the theta, that is the difference of the velocity with respect to the phase velocity, if we define the wave phase in this form, we can convert this equation into the so-called pendulum equation. The equation of pendulum, pendulum, contain this sine function. And because of this, we have nonlinearity. So this is the nonlinear equation. And the solution of this equation has a typical motion of the trapping motion. And here, this S is additional term that we call inhomogeneity factor. And this S plays a critical role for the wave generation and wave damping we will see. And if this is an equation motion of a single particle, but we have many particles. But the basic trajectory of this particle takes this form. With different S value in homogeneity factor, its trajectory drastically changes. And with S equals 0, then it shows a very simple pendulum motion. Pendulum means we have the trapping motion here, oscillations. And we also have the untrapped particles here. So let's see this S equals 0 homogeneous case first. Okay. And here we have some width in the trapping motion. Particles oscillate with in velocity space. This is velocity, and this is phase. Phase means for this electrostatic wave, this is a position. And we call this width a trapping velocity. This width becomes important in describing the system. So now let's see how the particle moves. So if we put the particles, okay, better to use the laser pointer, sorry. Okay. So if we put the particle at the 0, theta equals 0, that means all particle has the phase velocity, start from the phase velocity. Then particles are stably trapped like this. And it shows this very, very nonlinear motion. But if we start a particle slightly off from this 0, then we see like this. All these particles are not trapped, but still they contribute to the wave resonance, and we find this kind of wave potential, which is empty here. So particle cannot enter this empty region, and we call this empty region electron hole. If we assume the electron, this is electron hole. Then let me show you the most typical example of the instability in space plasmas. Or well, even in the laboratory plasmas, if we put the two electron beams, okay, horizontal axis, this is the velocity. So we have electron beams. This is a distribution function. And we have many particles here, many particles here with different velocities. Then this kind of system is unstable, and two groups of particles mixed together, as we will see. We have, this is velocity and this is position. And here we have this strong mixing of the two beams, and we already find this strong wave potential, very large potential is being formed. And what is interesting is we can observe the coalescence of this potential. They are moving, but slightly different velocity. And the velocity are slightly different. Yes, so they mix together. Mixing of particles takes place, and they become the two potentials with a slightly different velocity becomes to get together and form the new potential with larger size. So if we observe this potential as an electrostatic field, then it looks like this kind of bipolar structure. Okay, so this is a case with very strong two electron beams. We will change the configuration of electron beam. In the previous case, we have the electron and ion together. One of the electron beam was with ions, and the other is offset. But the next one is we have ions at the center, and we have two electron beams. Then we have slightly different situation. As you see, we have the same formation of electron potential, but because of the presence of the ions at the V equals 0, we have two groups of particles, electrons. So electron beam moving forward and backward. In velocity space, they have different drift velocities. Then, although they collide, but they do not, they are not mixed. They do not coalesce each other. And kind of they are slightly modified when it collides with the coming particles, but they are not affected. So important point is if the two group of particles are very close in velocity, they may coalesce and get together. But if they are separated like this, they can remain under just a single beam. Okay, let's see the different case. This is a case which may occur often with plasmas with ion. The majority of the plasma is just electron and ion, called electron and ions. And we have this small electron beam. This is like a beam experiment in space. If we inject the electron beam in space, we have this like this. And let's see. Okay, so we have a small density electron beam. Still, we have the instability. And in this case, this is a Langmuir wave, and Langmuir wave takes a different phase velocity. So we have many waves here in this system. And we have particles moving at different velocities. So their phases mixes, and we do not find the solitary waves as we have seen. And this is the case with the uniform system. We assume the beam in the uniformly as the initial conditions. But in the next slide, we inject the electron beam from the left boundary, like this. And then, let's see, still we find generation of waves at different phase velocities. and structure is just like incoherent, what we call incoherent. We mixture of different waves, different phases. But situation changes if we increase the thermal velocity of the background plasma. Like this. Okay, we have the spreading warm plasma as a background, and then we inject the electron beam. Then waves being excited is limited at specific phase, specific velocity. In this case, we find formation of electrostatic solitary waves. And we find these potentials, they attract each other, and they coalesce because their drift velocity is slightly different, and the phase mixing occurs, takes place like this. See? So we assume this kind of interactions, generation of wave is occurring in space, in the boundary layers. And this is the observation by the spacecraft. Okay, so let me here talk about the coherence. We often say coherent wave or incoherent wave. That is, we refer to the phase of the wave. But in the case of wave-particle interaction, we can define the coherency with specific manner. When we say coherent waves, that means coherent wave-particle interaction, incoherent wave-particle interaction. That means the phase velocity of two waves are very close, and under the action of two different waves, particle here becomes chaotic motion, takes a chaotic motion, and its phases mixes. And because of this phase mixing, we have seen the coalescence of two potentials. However, in the case of what we call coherent waves, if their phase velocities are separated much greater than the trapping velocity, the size of this potential, then we call it the separability condition. Then we can regard each waves are interacting, performing like a single wave. And here we can say these waves are coherent waves. And now we have seen the change of the structures in velocity phase space. And what we have seen was a stable potential, stable static waves. But this stability breaks down when we apply the external E field, or if we introduce the inhomogeneity factor. We defined S value, and previous cases was S equals 0. But if we make the S non-zero value, then the trajectory becomes this shape. And let's see the motion of the particles. So particles are moving from the top side to the bottom side, and it moves around the wave potential, and they cannot get into the wave potential. And we find the formation of electron hole here. And this kind of electron hole is very important. They are not symmetric in phase. Okay? And we have the specific group of particle here, taking the specific phase. That means these group of particles at resonance velocity, phase velocity, they can form the resonant current, and that they can modify the wave field. They can give a wave growth or wave damping. So this asymmetry of the phase wave potential is very important. Okay, now let's see the another phenomena called Whistler mode chorus emission, and in that wave is very violent, very active, and that is active because of this electron hole, asymmetric electron hole. And the important point is we have non-zero S value, and how this S value becomes non-zero is a very important point. I will explain it. So this is chorus emission, rising tone. You are hearing the change of the frequency. And chorus emission occurs like a single emission, but it continues like this. We are looking at the spectrum, the frequency, time. This kind of emission takes place in the magnetosphere, equatorial magnetosphere, when the particle is injected to the inner magnetosphere. Okay, so let me explain the generation mechanism of this wave. I'm sorry for the equations, but in the previous slide, we assumed the electrostatic wave, and force was E field, electrostatic field. Instead of electrostatic field, we assume the V perp of the particle. Particle is gyrating, rotating around the magnetic field with perpendicular velocity and parallel velocity. And this perpendicular velocity and the wave magnetic field, we assume the wave, electromagnetic wave, propagating parallel to the background magnetic field. And this V perp and the B wave, okay, this causes V cross B Lorentz force. And that Lorentz force acts in the parallel direction. So that acts like a E parallel in the case we have seen. And for the S value, previous slide, we assume the external E field. Instead of external E field, we have the gradient of the magnetic field, this term, and this is important. This is d omega by dt. This is the frequency change. Normally, when we analyze the plasma waves, we assume constant frequency, but here we assume the frequency variation. And if we think of this frequency variation in the equation of motion, we can find this frequency variation contribute to the S value. And it changes the dynamics of resonant electrons. This is maybe the biggest contribution of this paper. And this frequency sweep rate is very important. These two terms, sweep rate, frequency variation, and gradient magnetic field, and they are divided by this is a wave amplitude. So wave amplitude becomes also important, especially if amplitude becomes large, this S value becomes small. Okay. So here is a simulation of the chorus generation. We succeeded. Dr. Kato and I were working on this chorus simulation for many years. And when we first succeeded to reproduce the chorus emissions with a computer, it took nearly 1 month. Also monopolizing the system with many processors, it took more than 1 month, I remember. But nowadays, it's much shorter. But about 15 years ago, we succeeded to reproduce this kind of emissions. Let's see. Waves are generated near the equator. And waves propagate in both sides of the equator. And if we observe it at different locations, they look like this. And what is interesting is this, the seed of the rising tone emission is formed nearly very close to the equator, and it is being amplified like this. So the essential part of the rising tone is formed very close to the equator. And it is observed when we move away from the equator as a very strong emission like this. The form of these emissions changes depending on some randomness of the system. So the frequency sweep rate plays an essential role near the equator. But as we move away from the equator, the amplitude increases. Then this term becomes unimportant for S. Instead, when we move away from this is the equator and this is off equator. When we move away from the equator, the gradient, we have the dipole magnetic field of the Earth. And the dipole magnetic field can be expanded as a parabolic function. And its derivative, we have the linearly increasing gradient like this. This is a magnetic field. This is a gradient. So gradient contribute along with this amplitude. So gradient works to amplify the waves generated near the equator. We call it convective instability. And we have seen the case naturally growing from the thermal fluctuation, and that is chorus. But in the magnetosphere, there has been an active experiment called VLF triggered emission, and we try to input the triggering wave at the equator in the simulation, and then we find the formation of this very pure, beautiful rising tone emissions like this. And in that, we find the clearly formation of electron hole like this. Let's see the animation of the generation process first. This is a frequency, and we have a triggering wave. From the triggering wave, we have this gradually rising, increasing frequency. New wave is generated, okay, from the upstream region. This is space, upstream region from the equator, and it propagates downstream. And exactly the same thing happens in the opposite direction, like this. And when we have this kind of variation, this kind of wave generation, let's see how the particle distribution is changing at the equator. This is a distribution function. As I said, particles, we are tracing about 1 billion particles. 1 billion, not million, billion particles. And it is impossible to plot all of them, but we calculate the distribution function from the large number of particles. And this is a result. In the velocity space, parallel velocity and perpendicular velocity, we have the distribution of particles. Red color represents the dense regions. And here, the initial, and then when we have the emissions for forward wave and backward wave, we have these depression. We find the formation of depression. And this depression corresponds to the electron holes we have seen. And in this simulation, if we look at carefully the top part of the distribution, where we have the very high energy particles, when the chorus is being emitted, we find some enhancement here. We find the electron hole like this, but we also find enhancement. If we take the cross section of this distribution, it looks like this. And we find this enhancement of the particles like this. So what is this bump? This is the electrons being accelerated. They are accelerated because of the nonlinear trapping. Wave is growing, moving around the wave potential, by the resonant particles moving around the wave potential, but some fraction of the particles get into the wave potential, and they take a totally different trajectory. They are guided by the wave, and they are accelerated like this. This is a test particle simulation. Test particle simulation means we assume the electromagnetic field evolution, and we trace the particle trajectory under them. And we assume the chorus emission with this is space and time, and this is wave amplitude propagating forward and backward, and frequency is increasing from 0.2 to 0.5 of the cyclotron frequency. And then, as you see, this is trapped by the wave potential, and they are being accelerated. And this kind of acceleration takes place for all range of energies, like 0.7 mega electron volt, 2 mega electron volt. Mega electron volt is velocity is almost close to the speed of light for electrons. So we find relativistic electrons here, and combining these test particle simulations, calculating all these trajectories, we performed this kind of acceleration simulation. This cycle means number of chorus emissions. If we assume one emission 1 second, that is kind of typical for the chorus emissions, then just with 100 or 200 cycles, we find the particles heated, accelerated from several tens of kilo electron volt to the mega electron volt. And this is exactly the formation process of the radiation belt. Around the Earth, we have the highly energetic particles that is called radiation belt, and chorus emission. It is just a wave, electromagnetic wave, but it can generate, it can form the radiation belts. And the radiation belt is very important for the activities of human beings in space. So chorus wave is not just a scientific interest, it is some application. Now, this is looks like another triggered emission or chorus emissions, but the chorus emission, we can hear the sound, kilohertz, okay? But here, the frequency is just few hertz. We cannot hear. But with just a longer time scale, we find these emissions. This is so-called the PC1 wave, and this is an electromagnetic ion cyclotron wave. This is exactly the same as the Whistler mode wave of electrons, and under the same mechanism of formation of a hole, we call it proton hole, and then we find the rising tone emissions. We copy the theory of the chorus emission to the EMIC wave, and we now use the so-called hybrid code simulations instead of standard peak simulation. Hybrid means ions are treated as peak and electrons are treated as fluid. These waves are due to the motion of ions, protons. And we have the observations in different regions of the magnetosphere. And this is a simulation result. We find the formation of a proton hole here, and we find these rising tone emissions. And we find the variation of this distribution function of resonant protons. And let's see the animation. Okay, just yes. So this is the dynamic spectrum. This is space and frequency. And this is a rising tone is being formed and propagated downstream. We have two bands. Here we have the helium gyre frequency. So we have the so-called proton band here, and here a helium band. Okay, and when we have this kind of wave, we have the particles distribution function near the equator is strongly modified. Yes, now wave is rising tone is being generated, and we have the proton holes, depression of particles, and at the same time, substantial amount of protons are precipitated, scattered into the lower pitch angle. V prop is small and parallel velocity is large, and this kind of particles moves along the field line and precipitate into the polar region, generating the so-called proton aurora. So this EMIC wave scatters protons. But this EMIC wave scatters protons, but not only protons, it can scatter the electrons. Sorry, this is a summary of the EMIC wave generation. And EMIC wave have this kind of sub-packet structures. But I wanted to say, EMIC wave interact with protons, but it can also interact, or it can scatter the relativistic electrons, especially when there are, as you can see, we find this red color is particles which is trapped by the EMIC wave. Particle means electron, relativistic electrons. MEV electrons are trapped by the EMIC wave, and they are scattered strong. This is pitch angle with respect to the magnetic field, velocity and magnetic field, and its pitch angle decreases. If frequency is constant, it slightly scatters to lower pitch angle because of the gradient of the magnetic field. But if we have this rising tone emissions, it strongly scatters the pitch angle and down to the zero, and it precipitated into the polar atmosphere. And it substantial amount of electrons scatters to the loss cone, and this works to cause depletion of radiation belt. So we now see the radiation belt is formed by the chorus, but it is scattered, depleted by this EMIC wave. Again, this nonlinear trapping plays a very important role, as well as frequency variation of the wave plays very essential role. Now, let's go back to the chorus generation system, mechanism. As I said, the S value inhomogeneity factor contains frequency variation and gradient of magnetic field. And which effect is important to understand which term is important, we eliminated the gradient of the magnetic field, and we assume uniform magnetic field. So this is a very simple system, uniform magnetic field, and we put the triggering wave and see how the wave is generated. And the important point, we have this system open, okay? This is open boundary, not a periodic. And when we analyze plasma waves, we often assume the periodic system. But here we have the open system, and this openness is very important. And as a result, we find rising tone emissions like this, also falling tone emissions. So the even with homogeneous magnetic field, we can have this rising tone and falling tones. Because of this frequency variation, we have the wave growth. And we can separate this rising tone emissions and falling tone emissions using the information of wave numbers in the system. And we find both rising tone and falling tone is growing in time, and in the velocity phase space, they form the electron hole here. And for the falling tone, we have the electron hill, electron enhancement. In both cases, we have larger number of particles, larger number of electrons here, and they causes the wave growth. So we can understand when we have this kind of distribution function, this is FV parallel distribution function, starting from the resonance velocity of the triggering wave, we have this depression, and we have electron hole, and the electron enhancement, like electron hill, and this is an unstable system. So we have these rising and falling tone emissions. Okay, finally, let me show you this special case. Chorus emission is generated outside the plasma sphere. In the magnetosphere of the Earth, we have the Earth and atmosphere, ionosphere, and then plasma sphere. And up to the plasma sphere, it is rotating with the Earth. But outside the plasma sphere, we have the regions, and in that region, we have the chorus emissions. But in the plasma sphere, where we have the higher density, higher electron density, we have Wisler-mode His emissions. And this His emissions has been thought, it looks like in the spectrum like this. And it looks like incoherent waves, okay? But if we analyze it carefully with higher time resolution, we find it consists of rising and falling tones, small, short rising and falling tones. We have separated this simulation result by the peak, and we have separated forward wave and backward wave. And if we take the specific frequency range, then we find these evolution of the wave packet. This is space and time, and the wave packet is growing. And if we take a frame of reference moving with this group velocity of the wave packet, here this is a plot. We have increasing wave amplitude, increasing frequency. And if we check the growth rate of this wave packet, it grows very rapidly, a very large growth rate. And this growth rate is in agreement with theoretical analysis, and that value is much greater than the linear growth rate. In the plasma physics community, space plasma physics community, we often discuss the wave generation in terms of linear growth rate. But the linear growth rate is for constant frequency wave. If we have the frequency variation, then the growth rate becomes different. And we have this nonlinear growth rate, and its value is greater. And His emissions, which looks incoherent, but actually they are separated. They exist at the same position at the same time, but they are slightly different frequencies, and that frequency difference corresponds to the difference of different resonant velocity, and that satisfies the separability condition we have seen, and they can regard it as a coherent waves. Okay. And finally, just let me introduce my recent effort with a group of Peking University. We are applying the this idea of wave particle interaction to the much greater, region. This is the Earth, and this is around the Earth. We have ultra low frequency wave, ULF wave, with a period of few minutes. And with ULF wave, we can think of the ULF wave resonate with relativistic electrons. And as you see here, we find the nice trapping motion, nonlinear trapping motion. Actually, this trapping motion is more complicated than the case we have seen. It has additional term, and it is kind of modified trapping pendulum equation. Okay, here's a summary. And I just wanted to show the nonlinear trapping. And this computer simulation I've been working on can be summarized by this nonlinear trapping. And what we are finding is the frequency variation is essentially important. And finally, the system must be periodic. Must be open system. Yeah. When we had a small amount of the supercomputer power is not so large, we have to assume the periodic system. In that periodic system, we could not reproduce this rising tone chorus emissions. But nowadays, we have a much greater power, and we can take the many particles and many grid systems. Then we can make the system open, and then we are finding the frequency variation. And because of that, a wave is growing as a chorus wave. I really appreciate the advance of this supercomputer power. And before stopping, just let me show you the other future studies, which is not completed yet. Yeah, this simulation shows the formation of a solitary wave in two-dimensional system. In observation, we often observe the perpendicular electric field. And in that case, we need a two-dimensional system, but two-dimensional system require a much greater number of supercomputing system resource. So we need to study this kind of interaction in two-dimensional, and ultimately a three-dimension is needed. And even for the chorus case, chorus wave we have seen is just parallel propagation. But the wave propagation direction can be oblique. And with oblique propagation, we find the gap between the higher frequency and lower frequency separated by the half of the gyro frequency. And we have the gap. There occurs a damping. Well, theoretically, we expect a damping, but the self-consistent simulation has not been achieved yet. We have done some test particle simulation, but self-consistent simulation is a kind of future study. I think this is some review articles I have written so far. Okay, that's all. Thank you for your attention.
Okay, thank you very much for a valuable presentation today. We understand that the supercomputer simulation is a powerful tool for understanding space plasma. Let me move into question and answer period. Do you have any questions or comments? Oh, I have a question. What is the most impressive finding?
Well, biggest impressive finding is this rising tone. When Dr. Kato, Professor Kato came to me, and when we saw, it was really, really surprising.
Okay, thank you very much.
Ujihara-san, yes.
単なる数値計算の好奇心で聞くんですけど、その PIC を選んだ理由って何かあるんでしょうか？スパコン向きとか。例えば天体物理だと SPH とかスムーズとパーティクル法とか、使ってますっていうと、利害と欠があれば教えてください。
ピックシミュレーション、パーティクルインセルシミュレーション。
はい。
パーティクルインセルシミュレーションは一番スモールスケールのですね、 we can study the peak. The question was why we choose the peak simulation. Peak simulation can resolve the highest, say, small scale interaction, like a Whistler mode wave and Langmuir wave. In that, yeah, that is a scale of the device scale. So in this case, peak simulation is the best.
わかりました。
Thank you for your question.
そう、そのスケールのインタラクションをやっぱ解きたかったっていうのは動機なんですね。
Yes.
あとスパコンに実装するにあたってなんか苦労したとことか難しいとことかありますか？
Well, the most difficult part for supercomputing is how to parallelize, how to achieve the parallel computing efficiency.
はい。そうなんですけど。
Yeah, that is not, especially peak simulation, particles move the different regions and different grid points. So it causes a random access in the memory system. And that causes a lot of strong load to the computing system. So parallel efficiency cannot be high.
そうですよね。だから、やっぱりアクセス、隣のメモリへのアクセススピードとか結構重要なんでしょうけど、どれぐらい改善されましたか？
ですね、when we introduced a special algorithm invented by late Professor Nakajima, all help, that algorithm is genius, and we have the kind of very scalable supercomputing. But for this simulation I have done, we did not implement. So we just use the minor parallel parallel computing effort.
なるほど。そういう役割分担があるわけですね。ありがとうございます。
はい。Okay.
Yes, 山本さん。
山本、please.
はい。どうも大変面白いお話ありがとうございました。
ありがとうございます。
ちょっと全然違う分野かもしれないんですけれども、最近核融合っていう話がだんだん盛り上がってきて、で、あれはプラズマテクノロジーですよね。で、先生のこういうご研究がね、そういう分野に対しても何か貢献するというか、影響を与える部分っていうのはあるんでしょうか？
はい、もう日本語でございますけれども、
はい、
あると思います。最近核融合分野の実験室プラズマでもですね、特にレーザー核融合みたいにですね、電磁波でプラズマを加熱するとか、そういうことが行われているわけですから、その電磁波がですね、周波数が落ち着かず、安定せずにですね、まさにこのコーラスのように不安定になって周波数が上がるということが観測されています。ですから、どうしたら不安定になるかということに対する理解というものが、こういう自然界のコーラスを調べることによって、我々深めているということで、同じ考え方が核融合の分野でも適用できると思いますし、実際最近それが注目されてまして、共同で研究会も行っております。
先生の分野だと、プラズマの外側にやっぱりバウンダリがないっていうことが非常に特徴で、今もコンピューターシミュレーションでは、それが実現できたから、新しいステップが踏めたっていうふうにおっしゃった。で、核融合ではそれが非常にちっちゃい領域で、そういうふうなものが起こりうるっていう、そういう条件が。
そうですね、核融合のデバイスの壁と、それから本当に起こるコアの部分との間には、不均一性というか、
なるほど。
直接の周期境界のようなものじゃなくて、やはり境界があるわけで、境界というか、自由境界みたいなものがあって、でそういう場合には、こういうチャーピングが起こるということがあると思います。
はい、どうもありがとうございます。
Thank you very much. It's time to close. I'm sorry, maybe we have to close. Okay, if you have a question, please send email to Professor Omura. Thank you very much for your participation, and I'd like to express my special thanks to Professor Omura.
Thank you very much for your attention.